Good morning. In this presentation, I'd like to share with you some model results for 3 alternative management scenarios designed for the Middle Carson River Basin. And for the duration of this presentation, when I use the term Middle Carson River, I'm referring to Eagle, Dayton, and Churchill valleys, and even more specifically from the Carson Cily stream gauge to just below Lahontan Reservoir stream gauge. The motivation for this study was realized in 2007-2008 during the economic boom here in northwestern Nevada. And at that time, increased development was stressing the available water resources. And it was observed that there were long-term drawdowns in some of the groundwater monitoring wells distributed throughout the Middle Carson River reach. Of course, those concerns were mitigated by the economic downturn in 2008, but nevertheless, because it's understood that growth is expected to continue at some time or another here in northwestern Nevada, it's prudent to study the available groundwater resources within the Middle Carson study area. And with our baseline simulation, we investigate alternative management scenarios that could be realized when growth resumes. Here we can see a depiction of the population growth within the Middle Carson River reach, and soon we'll see another set of data points appear when the 2020 census completes. But in general, we can see a real rise in the population starting in about 1960. The long-term drawdown that I alluded to earlier was witnessed on the west side of Eagle Valley, and specifically within this region over by Western Nevada College or on the western side of town. These results come from a study published in 2011 by Doug Maurer. And in it, he outlined or delineated areas where the groundwater decline between 1964 and 2009 was either 10 feet or, in a more extreme case, up to 40 feet over on the west side of Eagle Valley. In Dayton Valley, the long-term drawdown was just to the south of the town of Dayton and was to the tune of 10 feet between 1995 and 2009. In western Churchill Valley, long-term drawdown was observed to be well north of the river in the Misfit Flats area. And here the long-term drawdown was on the order of 5 feet. You can see that by the crosshatched area, the yellow crosshatched area, and up to 10 feet in the area that's crosshatched in black. Another motivating factor for this study are the observed trends in river flow at the Carson Cily stream gauge. The plot on the left, the green dots are showing the mean daily flow for each year starting in 1940. Also shown on the plot on the left is a moving average line. And we can see the downward trend in that line starting at roughly 400 CFS in 1940 and dipping below 300 CFS as we move closer to today. Similarly, we can see that in May and June, the 7-day minimum flow in those 2 months has also markedly reduced between 1940 and today by more than 50%. So if we take all these concerns together, that is the increased pressure on available water resources by increases in population, the observed long-term drawdown in the groundwater stored within the Middle Carson River reach, and the diminishing flow trends within the Carson River, we need to look at alternative management scenarios in order to preserve the long-term viability of the Carson River system. So later in this presentation, we'll explore three alternative management scenarios, and these are referred to as the 40-40-20 scenario, the reclaimed effluent scenario, and exercise of existing groundwater permits scenario. Real quickly, to give you a sense for what's in the model, if we start with Eagle Valley, we do explicitly represent pumping wells, which are shown by the yellow circles. And then over here by the river on the east side of Eagle Valley, you'll notice two green dots. These are induction wells, and these are explicitly represented within our model. The green areas are showing you where we simulate crop water use, or we simulate ET. The yellow squares are showing you where stream cells are located within the finite difference model. And of course, those cells are going to simulate groundwater surface water interaction. And then along the mountain front, we do simulate varying degrees of mountain front recharge. Many of these same processes are represented within the Dayton Valley portion of the Middle Carson River model. That is, we simulate pumping from supply wells, or the yellow dots. There is one induction well represented in the model, and that's roughly in the center of the model. You can see it kind of near where 6 Mile Canyon flows into the Carson River. We also simulate stream cells, cropped cells, and mountain front recharge. Moving further east, many of the same processes are represented in western Churchill Valley, as you can see here. And then if we go to what is essentially the eastern extent of the model, the largest feature that is explicitly represented within our model is Lahontan Reservoir. And you can see that by the blue shaded cells. And so as the stage in Lahontan Reservoir rises and falls, we're going to represent that explicitly within the model, and the resulting groundwater surface water interactions are going to be influenced by the change in reservoir stage. After developing the Middle Carson River model, we then calibrated it, and owing to time constraints, we will not get into that today. But with the calibrated model, we can then evaluate various alternative management scenarios, and 3 have been investigated with this model, the first of which we refer to as the 40-40-20 scenario. The 40-40-20 scenario is by far the most complex of the 3 investigated scenarios. In a nutshell, this scenario was looking to convert surface water rights to groundwater rights. And when a surface water right is transferred to a groundwater right, the constraints regulating the maximum amount of monthly diversion for irrigation remain intact, or remain associated to the now groundwater right. A general description of the rules governing the timing and maximum diversion amounts are given in the Alpine Decree. Under the Alpine Decree, maximum surface water diversions may not exceed 40% of the total water right during April, nor can they exceed 40% of the total water right during May. And finally, that leaves or means they cannot exceed 20% of the total water right in June. Irrigators could choose to irrigate less than the maximum amount each month, and in so doing, irrigate beyond these 3 months so long as they do not exceed the total water right and remain in priority. Monthly allotments of 40%, 40%, and 20% in April, May, and June respectively give this scenario its 40-40-20 name. The general intent of the 40-40-20 management scenario was to decrease municipal pumping withdrawals in April, May, and June in areas of long-term groundwater level drawdown that I showed in some of the previous slides, as well as to provide a reliable source of water for new residential development. Thus, reductions in pumping from municipal supply wells were offset with increased pumping from the induction wells using the transferred surface water rights. At the beginning of July, when the water right transferred under this scenario are exhausted, simulated pumping from existing municipal supply wells are increased to levels above their baseline pumping amounts to supply not only the original demand, but the additional demand associated with the newly permitted residential development based on the transferred water rights. Because the transfer of water rights from surface water to groundwater for augmented induction well pumping alters the timing and amount of return flows from the previously flood irrigated fields, model results from this scenario were compared to those of the calibrated baseline model to assess downstream effects that arise from the change in water use. Selected ditches for which the water right transfer was used in the 40-40-20 scenario included a partial reduction of irrigated acreage below the Mexican ditch and a complete reduction of irrigated acreage served by the fish ditch in Dayton Valley. So what might this look like in a pictorial sense? Basically, the area in red is showing some new hypothetical expanded residential area. And during the months of April, May, and June, that new expanded residential area is going to be served via increased pumping from the induction well. However, because the amount of water transferred from the surface water right to the groundwater right exceeds the total demand of that new hypothetical expanded residential area in April, May, and June, the additional water pumped via the induction well can also provide to existing homes and therefore reduce the amount of water that is needed from the historical production wells. Then in July through March, when the transferred water rights are not available to the induction well, the new expanded residential area is supplied from additional pumping from the production wells. So the impact of this scenario will be viewed in three ways. The first is to look at the overall impact on groundwater levels, particularly in those areas that experience long-term drawdown. Look at the change in groundwater surface water exchange patterns, and finally look at the impact on flows at Fort Churchill. If we start by looking at the change in groundwater levels under the 40-40-20 management scenario, we see a rebound in groundwater heads on the west side of Eagle Valley, and that is because we are reducing the stress on those supply wells on the west side of town owing to the increased pumping from the induction wells on the east side of Eagle Valley. However, there is a pocket where there is increased decline, and that is owing to the specifics of how the pumping was distributed within the scenario. Also, we can see that there are additional losses from the river to the aquifer, and that is in close proximity to where those induction wells are going to pull additional water during the months of April, May, and June. Moving east in Dayton Valley, we can see that there is some additional decline, particularly under the fish ditch. And if we pause to think about that for a moment, we know that that ditch was completely dried up, so there's no longer recharge occurring from irrigation, which is going to likely contribute to a reduction in the groundwater heads under this scenario. Under 40-40-20 management, we do see a slight increase in additional losses occurring from the river to the aquifer system within Dayton Valley. Under the 40-40-20 management scenario, the flows at Fort Churchill decreased. The average annual decrease in flow at Fort Churchill is roughly 521 acre-feet per year. A separate sub-scenario was run for 40-40-20 management, whereby under the Mexican ditch we decreased the potential ET by half to simulate a change in land use associated with 40-40-20 management scenario. And when we did that, there was an overall increase in flows at Fort Churchill predicted by the model to the tune of an additional 162 acre-feet per year flowing past the Fort Churchill gauge. A few things to remember in the 40-40-20 management scenario. The transfers were 100% consumptively used. However, the inefficiencies that were previously associated with the diverted water do stay in the river. So any seepage that occurred from diverting that water into the Mexican ditch or the fish ditch, that water is going to be left in the river. Additionally, recharge associated with the flood irrigation under the baseline scenario, that water that would then slowly make its way back to the river will instead remain in the river. That is, it will never have been diverted under the 40-40-20 management scenario. This scenario does not account for adjustments in downstream diversions based on additional water being left in the river because it's no longer diverted by Mexican or fish ditches. The second of the three investigated alternative management scenarios is titled the Reclaimed Effluent Trade Scenario, and fortunately isn't as complex as the 40-40-20 scenario. This scenario focuses on effluent, treated effluent, from a wastewater treatment plant in Dayton Valley. Between the months of April and October, treated effluent is contracted to be delivered to a golf course. But in the months November to March, this water is released to a rapid infiltration basin that then contributes to groundwater recharge that subsequently flows back to the river as groundwater discharge. So in this scenario, we relax supply well pumping by an equivalent amount of what's released to the rapid infiltration basin. And that relaxed supply well pumping occurs only during November through March, when that water is not contracted to be delivered to a golf course. The resulting impacts of this scenario on the groundwater heads within the area of long-term drawdown, highlighted by the red polygon in the lower left portion of the map, are quite subtle. The time series plot on the left is showing the simulated heads in the area of long-term drawdown in the baseline, that is the black line, and it's also showing the simulated heads in that same area under this scenario. When we difference the two time series shown in the previous slide, we get the time series shown in this figure on the left. And we can see that the rebound varies between hardly any rebound to roughly half a foot or more of rebound in the area of long-term drawdown. The effect that this scenario has on flows at the Fort Churchill gauge is shown here. If we consider the absolute flows shown in the figure on the left, there is no perceivable difference between the total annual flows in the baseline simulation compared to the total annual flows in the scenario. However, if we difference these bars and zoom in as shown in the plot on the right, we can see that the total annual flows in the scenario have decreased by roughly 50 acre-feet per year early in the simulation and have resulted in slightly increased flows in 2009 and 2010. This may be the result of relaxing the supply well pumping by an amount equivalent to the increase in induction well pumping in November through March that captures the water released to the rapid infiltration basin during these months. The final scenario we will look at today is the exercise of existing groundwater permits to varying degrees. This scenario is by far the most aggressive of the three investigated scenarios. To start, consider the blue bars. These show the baseline simulated pumping in all three valleys. And in each case, you can see that it's less than the permitted pumping that's labeled above the three groups of bars. So this scenario looked at incrementally increasing the baseline pumping up to the full permitted groundwater rights, and then looking at the impact of that on groundwater heads as well as flows at Fort Churchill. So two of these incremental increases are shown here. On the left, this is the impact on groundwater heads in Eagle Valley under the 25% incremental increase in pumping. And we can see that there is widespread declines in groundwater heads throughout Eagle Valley. If we were to then look at the 100% pumping increase scenario, that is full exercise of the permitted groundwater rights in Eagle Valley, there is even more drastic drawdowns within Eagle Valley, up to 20 feet of drawdown on the western side of Eagle Valley. The additional losses from the Carson River under this scenario are more significant than we've seen in the other scenarios, and this will culminate in significant decreases in flows past Fort Churchill. A similar situation is seen in Dayton Valley as we saw in Eagle Valley. Under the 25% pumping increase, we do get additional groundwater drawdown throughout Dayton Valley under the 25% pumping increase scenario. Under the 100% pumping increase or full exercise of permitted groundwater rights, there is widespread and significant drawdown in Dayton Valley of between 5 to 20 feet of drawdown over the 10-year simulation period. We also see significant losses from the Carson River in Dayton Valley under this scenario. In western Churchill Valley, the story remains the same. And in particular, if we focus our attention on the 100% pumping increase scenario, there is significant drawdown throughout western Churchill Valley when the pumping is increased to its full permitted amount. When groundwater rights are fully exercised, the effect on groundwater surface water exchanges along the Carson River in western Churchill Valley are mixed. And this is likely because pumping upstream has so lowered the river and the stage that surrounding groundwater levels may now be above the river stage, causing slight gains in stream flow along the Carson River. Increases in pumping throughout the modeled region result in lowering the heads in the vicinity of Lahontan Reservoir. As a result, there may be additional losses from the reservoir to the groundwater system. One way of integrating the cumulative impacts of increasing groundwater pumping in the three valleys represented within the model is to look at the flows or change in flows at Fort Churchill relative to the baseline simulation. And here we can see that in all four of the sub-scenarios within the exercise of permitted groundwater rights, significant reductions in flow past the Fort Churchill gauge. And in the most aggressive of these four sub-scenarios, the 100% exercise of permitted groundwater rights, you see flows diminishing at Fort Churchill to the tune of 12,000 acre-feet per year. A few parting thoughts to wrap up this presentation. First, the alternative management scenarios that were investigated were developed in cooperation with local stakeholders. They demonstrate the effective use of a groundwater model to evaluate the impacts of alternative water management scenarios. In all of the investigated scenarios, we saw impacts on groundwater heads, on groundwater surface water interaction, as well as on flows in the Carson River at Fort Churchill. The 40-40-20 and effluent trade scenarios had the smallest impacts on these three aspects of the system. The most aggressive of the scenarios, the full exercise of permitted groundwater rights, had the largest impact on groundwater heads and flows at Fort Churchill. It significantly lowered groundwater levels throughout all three valleys, as well as significantly reduced flows at Fort Churchill. The reclaiming of wastewater effluent had the smallest impact on Carson River flows relative to the baseline conditions. Thank you for your time.